tubes. We also had to add all the pressure taps to those tubes as well, so we can get all the points marked out. And once we did all that, we had to mount that in and run our data. So once we got all of our points collected, we were able to do all the other stuff. So some of the methods that we would be demonstrating is the modified cars, also collecting data as well, showing our calculations for that data, and hopefully again our end goal of showing that the downforce is applied. So as you guys can see, this is how our car was set up in the wind tunnel. We mounted it to the metal pole with a base plate, and that did seem to hold throughout the whole testing. And as you can see, we had our tubing shooting out the back of the car, which I'll get into more as we go further down the line. So we had added 3 pressure taps to each car. We had the front, the top, and the back. All of this was all in a unison flow. There was no curvature to it. It was all in a straight line, and we wanted to do that on purpose so we would have no general other negative effects toward non-streamlined flow. As you can see, the first point we drilled in here. Our second point is on top, and our third point is in the back. And when we came to lab testing, this is how we had our car set up. Pretty much we stripped out all the interior of the car, and we only used the shell of the car. And with the shell there, we put all the tubing out the back. As you can see, we had dremeled out the back where the exhaust was in the car, so it was almost like a true exhaust almost. So this is the raw data we got from initializing our test. Pretty much the only thing that I want everyone to see here is the difference between the base model and the one with the spoiler on the back. So if you look at the lift, this is a negative, so it's a negative 0.5 pounds of lift, meaning that there's downforce applied. So that is the base model car, so there's just a natural downforce due to the car's shape and size. And then when we added the airfoil or the spoiler to the rear of the car, it is negative 0.45 pounds of lift, meaning that it gains 0.3 pounds of lift or of downforce for the spoiler, which is pretty significant due to the fact that the car is, a 1/24th mile scale car.
So here's our pressure distribution graphs. These graphs show you the pressure on each of the taps changes as the fan speed increases with and without the wing being attached to the car. As you can see, the main one that got affected was the roof, just because due to the increased pressure as it went over, and then just the regular flow throughout. And we have our pressure difference versus speed. This was based off the manometer value. This is based on the reading showing the pressure difference varies with the speed, showing the changes in airflow and downforce. There wasn't a very big change, just due to the just like the curvature of the car from front to back. It's almost the same. The only effect was the rear, which is where most of the downforce was created. So here we have our aerodynamic effect, as I was just saying. These graphs show the effect the wing had on the car. Main effect is lift, as we can see right here. Drag, there was only a slight increase, just because as you increase, decrease lift, you have a slight increase in drag just due to the wing pulling the car back slightly, but not too much of an effect. But as we can see here, with no spoiler and with spoiler, we had a pretty big increase in our lift. So here we have the coefficient of drag graphs. Again, as I said, we had a pretty significant change in our coefficient of lift from front to rear. This shows the true efficiency representation that the wing had. As the speed increased, the coefficient of lift from front to rear increased, which is, a decent increase in negative lift at those speeds. This is to show the comparison of aerodynamic efficiency of the wing added to the vehicle. Again, all the other effects were pretty normal, and the drag was also pretty similar.
So moving on with this, these are the simulations we found online. We were trying to achieve this. This is kind of what we were working towards. Obviously, we can't show this type of wind flowing through in that wind tunnel with no way of showing that, of no fog. So this is what we're trying to achieve, and that's on our base model we're trying to go towards. So this is our testing that we've done. The videos pop up here.
Try clicking.
Nope. Try
second. I'm sure everyone's going to make sure they're connected to the Wi-Fi now.
Yeah. Okay, sorry about that. So diagrams, and then this is our videos of our testing. So this is our base model car. As you can see, all of these tests are run at 100 miles an hour roughly, which is roughly around 45 hertz in there. So we kind of wanted to simulate like a real world scenario of the car speeding. So as you can see here, it is a little bit wobbly in that base model, but compared to the next model, or with the one with the spoiler, this one is a lot more stable at high speeds due to that spoiler adding stability and downforce to this car. So you can see the wheels are going a little bit crazy there. It is very fast. It is 100 miles an hour again as a model car. So that's kind of the difference. We do have the top views of each car as well, which we will show coming up here once this video finishes. And that really does show the difference between how the stability is affected. So looking at our base model car, if you look real quick, you can see how much it is wobbling in the front. Once the speed does pick up, it does start wobbling. You can barely see it a little bit, but it really does start to create a lot of turbulence and disturbance within the air. So with that being said, we do have that spoiler version, which we did say is a lot more stable, and we will show you that the top view is a lot more stable compared to this base model view as we wait for this video to finish. Hopefully. So compared that to our now spoiler car, this one is extremely still. There is no movement, no turbulence. It is very stable at this high rate of speed, which does conclude that it is more stable than our base model car, and that is exactly what we were trying to shoot for. So we're very, very happy to see this result, as this is what we were working towards. So in conclusion of our lab, we did see the effects that the spoiler had for the lift and the drag, and we did see that a spoiler does make a difference when it comes into aerodynamics. We also did see that wind speed does affect a lot of disturbance, if that's including in lift or drag or all the coefficients. Also, it is shown now that the spoiler does add performance enhancing to it, which is awesome to have, and that we're able to see this in a real world setting.
So here we have the calculations for our lift and drag. I added the calculations for our coefficient of lift and drag. For the lift value, we took our values from the machine. We took them in pounds and I converted them into newtons. And then I have the dynamic pressure. Right here's the calculation for it. I took rho from a calculation that we got from the wind tunnel from our previous lab. And I got our static pressure, our delta P for pressure. We took the static pressure off the roof in pascals and subtracted from the stagnation pressure at the front. And then this is the molar mass, which I got the value off of Google. Then I got the gas constant, which is 287 joules over kilogram per Kelvin. And then I took the temperature. We took it from Fahrenheit to Celsius to Kelvin. And then this all got a value in slugs into kilograms over meters cubed. And then I converted it into slugs over feet cubed. And then we took our velocity based off the hertz and converted it into feet per second, and then 2 meters per second. And then the area is based off the wing of the vehicle, of the car. I took the span times the chord, which is the length of the wing over the width of the wing.
So when it comes to sustainability and real-world applications, obviously with adding some type of aero to a car, this can improve fuel efficiency, which also helps with the high rate of speed. As you guys saw, that car is much more stable at high speeds, meaning that the engine is technically working less sometimes, which could improve gas mileage. Also, it does optimize the airflow of the vehicle. As you guys did see, that again, that high rate of speed, that car was very stable, which creates better flow, meaning that there's no disturbance within the car. Also, to conclude on that, the stability, when there is higher rates of speeds, it is less dangerous. It is actually a safer application. So that's something to definitely include in a real-world application, is why we do want aero packages on cars. Things that we learned and gained from this. So we learned, obviously, this entire year we were doing fluid mechanics, and we learned the study of fluids, including following the path of fluids as we saw in our calculations. Everything that we learned throughout this year, we can apply into real-world settings. As you guys see, we did a model car, and that is going to be working for a real car. Also, taking this model car and analyzing it, see how the flow works and how all these paths are working is another thing of fluid mechanics. Also, we can also see that the study of aerodynamics with the lift and the drag is another thing to include there. Some of the future recommendations that we do have, it would be nice if there was temperature control zones within the wind tunnel, maybe like a heat gun or a sensor with a monitor reading, seeing that there is changes in temperature. Within my working setting, we use a lot of heat guns, and we can see difference in temperature and sometimes pressure. So it would be cool to physically see that as the air is flowing over the car. That's one thing. Another thing is physically seeing the airflow of the vehicle, if that's due to us adding strings or even some type of steam or fog within the wind tunnel. I do know it is a closed system, so it would fog up and you would be unable to see the car, but it would be really cool to see that in an actual working setting. So when it comes to our discussion here for the conclusion, we did compare the two models, and we did see a lot of gain that we got from it. We could see the difference of how much that did make. As we can apply this to our real world, as Mario said, he is into cars. I am also into cars. We'd like to build our one track car one day, and we can apply this knowledge that we learned using this model into a real world setting as we would like to build a car. We did have some human error. Obviously, this isn't a perfect simulation here. There is a little bit of error that we have to work around, but it's nothing too corrupted to our data. We don't have any misinputs. Also, it taught us how to apply an aero package to a car and how to really analyze it and make it work. Any questions, comments, or concerns?
We could have done flow visualization, but we could have done flow visualization, but there's always so many fun things we could be doing. Maybe we'll do that next time.
What would you recommend?
Yeah.
I've got a bubble unit, so the first thing I would try is bubbles, just because they're neutral buoyancy, small bubbles, so you can see the flow, but they do break before they get all the way around, so you don't load up with fog. The tails, the little strings, that's another great idea. It takes time to carefully glue a short piece of string on a vehicle. You got to keep it small because a small string on a car represents a big rope on a real car. But it does give you a visual of which way the wind is blowing across that surface, and it's something interesting to look at.
Mm-hmm. Mm-hmm. Well, anything else?
Questions?
Well, thank you. Thank you.